Okay, some of the other methods of direct reading of fastener tension, load cells. And of course this PLI preliminary or preload indicating washer that I described in the washer section is a mechanical load cell assembly, and those can be used. But of course in a lot of assemblies you don't have room enough to put all that stuff in, because the amount of deformation in them has been correlated to specific tension load in the bolt. Now the Skidmore-Wilhelm bolt tension measuring machine, shown on the next page, has a load cell in it to give a direct bolt tension reading for an applied torque. Now it's a benchtop type setup, which can be used at a construction site. You just clamp it on to a beam and check some bolts, and then you determine the torque that you want to put in that particular batch of bolts and use that for an installation. This company is here in Cleveland. One of the owners of it attended last Fastener conference we had here. See, it's a little jobby. It just has the clamps over here that you can clamp it on, and it gives a direct reading of the number of pounds that you're putting into the bolt. So it is a way of determining torque. Now here's another one that you don't think of it as being a direct reading, but it is, and I use this one, and I'll cover it later in the rivet section. This is a high lock rivet, and or a lock bolt. It's actually a lock bolt, pardon me, rather than a rivet, because the shank does not expand on it. But it has it's a blind type fastener for installation, and you have a hex key that holds it in place while you crank the nut on. And when you get the nut to the proper torque limit, it is notched here so that it snaps off, breaks off. So that is a self-limiting type that they have determined the right diameter for them so that it will break off at the torque that you want. Now here's one that I mentioned earlier, the DTI bolt, and the guy who has that company was at one of our Bolting Technology Council meetings. This is a color-coded type bolt. It has a little gauge pin that's threaded inside it, and then it has an optical absorptance cell near the surface, and as the cell changes thickness, it changes color. So as you elongate the bolt, it pulls this gauge away from the cell and gives you a color-coded load indication. So you torque the thing until it shows red or whatever, and you're all right. But of course, the problem with a bolt like this, you can imagine how expensive it is compared to a hardware store bolt, and it's got to be big enough that you can drill the center of it to put that stuff in, so the minimum size for it is a 1/2 inch diameter. Now we move on to design criteria, and this first line is one of my pet peeves. I think that we don't spend enough time looking at something before we design it. We should think about it, look at it first. Now, of course, working with the research people around here, you usually do designs by an iterative process, because when they come to you about something, usually they don't know, and I'm not saying this as a degrading remark, they don't know exactly what they want, so they tell you what they think they want, and then you take it from there. And usually what happens is you, by iterative process, you come up with the actual requirements. And that's something that you should do on any design. You should sit down first and look at it, decide what you really need, and then look at the accepted design practices from both a layout and analytical standpoints to see what you should do. Now here's one of the questions that comes up sometimes is, diameter versus length on fasteners. And we're always faced with decisions on, do you use off-the-shelf stuff or do you custom design it? Well, a good way to look at it is to check and see what's available first, see if you can build your design around that without having to buy special components. And so one of the things that you look at is the length to diameter ratio of fasteners, because if you want to use a 10-inch fastener that's a 1/4 inch in diameter and you don't want to make it out of threaded rod, you're in trouble because you're going to have to get one that's custom made. Usually the L over D ratio is up to about 12, and it's limited somewhat by the capacity of the automatic screw forming machines, because you can't put a long skinny fastener through there and do it on an automated basis. So we have a table here that lists common fasteners availability. Now these are industrial fasteners, not aerospace. And the 1 asterisk represents the stock sizes of maximum demand. So you see, if you're in this area, if you need a 3/8 diameter with an inch or 1.25 inch length, you got it. 2 asterisks represents the ones less frequently used. So if you want, say, a 1/4 inch and an 1 3/4 inch length, you might have a little trouble. All the rest of them are considered specials. So if you want a 1/4 inch by 6 inch, look how deep a trouble you're in down here, because you can't get it unless you pay special for it. And I know we had some fasteners on a job that we did here one time that were 1/4 inch stainless steel that had to be, I believe, 6 inches or 5.5 inches or 6 inches long. We had to pay special for them, and it took a long time to get them. Now, when I say these are industrial type fasteners, on the aerospace fasteners, the lengths there are graduated in 1/16. You can specify a dash number that gives you the grip length of the fastener in 1/16. But just because somebody shows it in their catalog doesn't mean that they have it either. So if you need something that's an oddball type length to diameter, you still are going to have to pay special for it. Now here's a little handy dandy thing that once again I got from one of these guys at Martin when I worked there. And I've never seen this anywhere either, is a way of calculating the number fastener diameter. I put it in my fastener manual, so a lot of you guys have already seen it. But in order to calculate it, this is for inches, of course, you take 60 thousandths plus 13 thousandths times n, where n is the number of the fastener, and that'll give you the total OD of it. And the example I give here is a number 8 fastener. You take 60 thousandths plus 13 thousandths times 8 gives you a 164. So if somebody says, I got a number 6 or a number 4, you can calculate the decimal diameter of it directly that way, just by keeping that in mind. Of course, a number 10 is easy, because it's 130 plus 60 is 190. And for those of you who haven't seen them before, they even have number 12 fasteners, which is, I believe, works out to be 0.216 or something like that. The automotive industry uses them some, and I ran into some of them one time, and I couldn't figure out what they were way back years ago until I figured out it was a number 12. But they're not a normal one. Now, clearance holes for fasteners. For shear applications, the clearance should be minimized. And ideally, the holes should be match drilled, and the material thickness and fastener strength should be sized to make the fasteners critical in bearing rather than shear. That means that if you pull and shear on the joint, that the fastener is stronger than the material it's in, so it will elongate the hole so it can load up the other fasteners. And in tension applications, you don't have to worry about that if you can assure yourself that you have enough tension in it, enough friction that the joint won't move. then you can have a looser fit on it. Then your main concern is to prevent the fastener head or the nut from pulling through the hole or something like that, or embedding in it. Now on the next page, Fred Yaris's group was kind enough to draw me up this little thing because I couldn't find one. Usually you try to steal stuff from someplace else for these to save yourself work, but we couldn't get by with it, so we had to make one. And this is a little drawing of a joint to illustrate the clearance hole gaps on fasteners and where it gets you in trouble. Now, this happens a lot. I'll go to this one over here to maybe it's a little clearer. This happens a lot where you have two pieces that one place makes one piece and somebody else makes the other one. Then you bring them back and you try to put them together. And this is what you get. Now, these are the different gaps. See here we have no gap on this. But look what we got up here, and look what we got here. So if you pull on that, the only way that these other fasteners can load up, like for instance here, since that one is up against the wall right now, in order for this one to load up, the hole has to elongate on here for that one to load up. So this is why that in a real shear applications critical design, you should match drill. And this is what the aerospace companies do. They'll take the pieces, they'll have a pilot hole in one, which is a smaller diameter hole than the hole that needs to be in it at the end. They will clamp them together, then they will use that pilot hole to go in with the proper size drill and drill the hole all the way through both pieces so that it matches perfectly. Drill with the same drill. And then you put it together and you don't have this problem. Now here's another one that we can run into trouble on, is mixing of the thread and material types. And this happens in design sometimes because you can have, say, 300 series stainless steel fasteners, and you can have A286 stainless steel fasteners, and you look at them, they look alike. The one has a strength of usually of 160, and the other one has a strength of 70. So you can get in trouble with it. So if the different sizes have fine or coarse threads on the same diameters, or I mean if you have them with the same diameters with the fine or coarse threads or metric threads, then you're in real trouble because to a mechanic all these fasteners look alike. And this happened on the CM1 job, if I recall. We had one that the guy couldn't figure out why it wouldn't go in the hole. And it was a metric coarse when I had him get a gauge and gauge it. And we had inch stuff around there too, so and the rest of the metric stuff was fine thread, I think, and this one happened to be a coarse. So this is asking for trouble because if something won't fit, somebody's going to try to make it fit when they put it together. Now, we covered the different strength levels and the fact that 300 series and A286 look alike. Stainless steels look alike, and even different platings on materials can be dyed to where they look alike. So next we go to the selection and positioning of a washer. And you got to pick washers that are large enough to distribute the load under the head or the nut without exceeding the compressive yield strength of the joint material. So you want a hard washer and a smooth one so that you know what your coefficient of friction is going to be. And if the internal diameter of the washer is much larger than the fastener, then you better try to center it to make sure that they will fit. Don't do one of those deals like I've seen people do before where they stack up a whole bunch of washers and then they got to jiggle them around to get them to fit under the head, and you might wind up with the thing embedding in the material on one side, and on the other side it's hardly loaded. Now, shear loads on a fastener group. this is something that I gave you a lot of verbiage on this to help you go through the stuff on your own. And so I'll just kind of hit the highlights on this. Number one, on where you have a pattern of fasteners, the first thing you want to do is determine the centroid of the pattern by picking X and Y axes and using unit areas times its distance to get the centroid. And although it's not a good idea to have fasteners of a different diameter, you can use them in this type of analysis by ratioing the diameters. For instance, the one I gave here, if I had 8 bolts of a 12-bolt pattern that were 3/8 and the other 4 are 5/16, you can ratio the shank diameters, and you use 1 for the one that you have the most of, and use the stress ratios then to give you a factor for the other one to use. This way you can calculate the pattern CG and get the loads on it. Okay, now in a lot of cases you'll have a symmetrical pattern, so you're okay. And but after you find the centroid, then you can get these sigma r squares for the fasteners, which will give you an equivalent moment of inertia, if you will, like calculating bending stresses. So we can move over to the figure, and I think I can talk you through that better. Here is a bracket that has an eccentric load on it here, R. Okay, now to get the and it's loaded just in shear. We're not putting any tension on it. So we have to transfer that to the CG. Of course, remember in strength of materials, you transfer a load to the CG. You have a direct load and a moment is what you replace it with. So you have this as your direct load, is just taking R and divide it by the number of fasteners. That gives you a load there. Now you get a moment, R times this value E, which you have to react. Now the way that you react that, you take these R values, which is the distance, this is the centroid since it's a symmetrical pattern. So you have 4 R values measuring here, 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 and here that are the same, and then you have 4 more that are the same from here to here, from here to here, up to there, and down to here. So now you take those and add them up. So you have 4 times R1 squared plus 4 times R2 squared. And that gives you your equivalent moment of inertia, if you will. Then you can find a load on the fastener by taking the moment times the radius to the one that is farthest away, and that then over the sigma r squared value that you calculated using those values, and you come up with another load. Now you take those two, since they're both in the shear plane, you combine them vectorially to get a resultant load P for a total shear load on the fastener. Then, of course, that takes care of the shear loads. Now, if you look at this value, this also would correspond to like a torsional formula, the TR over J, in which the sigma R squared is the R sub n squared is the equivalent of a polar moment of inertia J, except that the load that you get here is in pounds. And so, so then later on, if we have tension on something like this, we can combine it and get the total load using stress ratios. Now on edge distance and fastener spacing, this is something that's violated a lot. In fact, we've put out designs around here before that I have been very disappointed with because somebody used practically no edge distance on stuff. We won't mention any names, but Ron knows a guy that did this a few times on me. But here is the edge distance and fastener spacing, and these are nominal ones. So this is kind of what you shoot for. 2D nominal, where D is the diameter of the fastener. 4D spacing between fasteners. And the aircraft companies usually use a 2D plus 30 thousandths on their stuff just to give you just a little more edge distance in case you run into a problem. Now, one of the things that questions might be asked, well, if you have a shear lug, it doesn't have 2D. No, they're custom designs because they're usually pretty thick, and you go in and calculate hoop tension and shear tear out and that types of things on a lug. And that one is covered, I covered it in that the chapter I wrote for that textbook. It's not out yet because that was on fasteners and shear. And Shigley and a few other people also have coverage on shear and lug design. When you're talking about lug, you're talking about a crank that is fairly, crank type thing that is fairly thick. So, and usually you have, since it's a rotating type joint, it does not have a large edge distance, but it's got thick walls. Now here's something that I use to illustrate one of the other fallacies that we deal with in the engineering world. The development of bearing stress allowables. Bearing stresses, the normal way of doing it, you take, this sheet is thickness T. Now this represents a semicircular, there would be a fastener fitting in that hole, and this represents the way we're coming up with the bearing stress. Here's what you're actually doing. Because if you have a fastener in this hole pushing, the maximum stress is right here. So this represents that maximum stress here. It's 0 here because you're not putting any stress on it there. So what we normally do, and see Mill Standard 1312, which will be covered later on in here, gives all the different methods of testing of fasteners. Well, what they do, they put the fastener in the material and they test it to failure. When they get it to failure, whatever it failed at for a given diameter, they divide it by the diameter times the thickness of the material, that's your normal bearing area, and say that's the bearing stress. So if you look in Mill Handbook 5 or any of these books on bearing stress allowables, you will see that they are way above tensile element and tensile yield because they're a fictitious thing. What they are, they're a value that has been verified that you can use it for calculations and get by with it, but it's actually not a true stress. So if you don't have bearing stress allowables for material, since you see that these are proportional, P1 to the compressive yield equals P2 to the ultimate, and so on, you can come up with these just by taking 1.5 times the compressive yield or compressive ultimate of the material. Now that is a conservative figure, and because the actual test value will run around 1.7 for most of these materials, but Mill Handbook 5, if they didn't test to get the bearing allowables, in a lot of cases they'll just take 1.5 times the tensile ultimate or tensile yield and slap that in there for the bearing allowable because they know it's safe. All right, grip length and shear head and tension head on fasteners. Now, grip length is a very critical thing for shear design because that is the length of the unthreaded portion of the fastener. And when you have it in shear and you try to have no threads in the hole. So this is the thing that you do here, and you're supposed to size the fastener such that this doesn't happen. So you put a washer under the nut to allow tightening without running out of threads. Now the aerospace fasteners, the MS, NAS, AN, that type, are available with shear nuts or heads or tension heads and nuts to save weight on design, because if you're designing in shear, you don't need to have that much tension, so therefore you can go with a thinner head or a thinner nut. So we have illustrations of those in the next figure. Here is the grip length illustration. It's the bottom of the head to the end of the threads. And here is a shear head for a same size fastener. It's 1/8 of an inch thick. Down here it's 5/32 for a tension type. And notice two specs here that are called out, which those of you that are familiar with the fasteners, this is for J threads here, the Mill S8879, and this is for the class 2 or 3 and the standard threads. Here is a shear nut and a tension nut. Well, you see the shear nut is pretty thin, 203 versus 284 for the tension nut. So if you have a joint that is primarily shear, you can put in a little nut like that, and if you're using several hundred of them, it saves you quite a bit in weight on a airframe. Now here's another thing I keep coming back to. Avoid tapped holes. We covered the tapped holes and the type of taps, and here's some more reasons for avoiding tapped holes. Cost. Drilling and tapping a hole is expensive compared to drilling a clearance hole for a nut and bolt assembly. Inspection. About the only thing you do with a tapped hole is a go-no-go gauge and a minimum thread diameter check just by running a pin through it. And the root radius you can't measure very well. And since there's no such thing as a UNJ tap, the root radius is not rounded. If the hole's blind, it'll have burrs, shavings in it, everything else, and you're just stuck with it. Now here's the other type of design that you need to look at is tension loads on a fastener group. And at the time that I did this one, I couldn't find one anywhere in anybody's book, so I had to draw this one up myself. But it didn't get too fatigued during our scanning, so I guess it's all right. And here we have 8 fasteners on a bracket that has 2 different loads on it. It has a direct tension load, P1, and it has a shear load, P2, which also gives you a bending moment. So what you're trying to do is get the total load on all of these fasteners using the different loads that we have there. All right, the moment from the load, now here's another thing that's different from the other one is where do you measure R from? R is measured from the healing point for your sigma R squared. Because if this thing goes into compression over here, then you're not getting anything out of it for your tension load, so you can't use those 2 fasteners to carry the tension because they're in compression. They're not going to help you any. So what I did in this case, since it's a bracket and this is a flange sticking out, I said, okay, this thing is hard up to here, so I'll measure my R's from that point to the right. So I only have, for my sigma R squared, I only have 6 fasteners in it. But then for the total shear, I'm using all 8 of them, and for the total tension, I'm using all 8 of them. So in doing that, you can calculate the sigma R squared. You divide the load. I better leave this up here from my standpoint here for a moment. You can divide the load by 8 to get the shear loads. Then you can calculate the moment, which is the P2 times H. Then take the R7, which was the one furthest out, and use a sigma R sub n squared, and you can get a load then, a tension load from the moment. You have a P sub T on there, which you divide by 8 to give you the additional tension load, and you can go in then and calculate the total load in tension Then you have the shear load, which was the P2 over 8, and you can take those two loads now and go in and use stress ratios and calculate the margin of safety on the fastener for the total loading. See, here was a better print showing the one for the P sub m value, where you're actually getting the moment was the P2 times H, and that times R7 over the sigma R sub n squared. Now, the tensile load that you're preload that you're putting on these fasteners has to exceed P, or you're in trouble, because you don't want any joint loosening. Combined shear and tension loading. Now on this, you get all your summation of loads in the shear direction, you get all your summation of loads in the tension direction, and then you could use a mortar circle and work with it and get the principal stresses and that type of thing and calculate out an allowable and a margin of safety that way. But it's easier to use these stress ratios because that's doing the same thing. So what you do is you get two factors. You get a R sub S or R sub T here, which is the actual shear load over the allowable shear load for that fastener. Now in this case, you can work in pounds, you can work in stress, either one you want to, as long as you're consistent in your units. So you get a factor there. You get one from tension, the actual tension load over the allowable, and then you get a margin of safety, which takes the actual load over the one you calculated here, minus 1, to give a margin of safety. Now, what happens with these values, when you combine them, you get two values that had better be less than 1 for each one of them, because you don't want either one of them to be greater than 1 or you're in trouble on the design. So you have these, and they have exponents, x and y. Now it depends on your degree of conservatism as to how big an exponent you use for those, because of course the bigger the exponent goes, the more unconservative you become, because the sum of those two have to be less than 1 in order to have a positive margin. Because margin of safety and safety as a safety factor of 1, if you will. So a margin of safety of 0 is a safety factor of 1. So therefore, if people say, well, gee, I got a margin of safety of 0.03 on that part, well, that's still good, because that's 1.03 safety factor-wise. And that's the way the aerospace industry has been doing it ever since Glenn L. Martin. So here are these curves that you can use, and it depends on how conservative or unconservative you want to be. Now, for if you're the belt and suspenders type and want to make sure everything's all right, you can use a straight line version here, which is just uses no exponents at all, and calculate the margin, and that one is a lot safer. If you want to get more unsafe, you can go further out on these by squaring and cubing these ratios, and that will give you a better margin of safety for a given load. Now here's one that is another one that has always bothered me, because in school I never did like the way these professors went through horizontal shear stress and said, and the determination of this is an exercise left up to the student. So anyway, I went through and developed this for the lecture that I give on fasteners in shear, because it had always bothered me that nobody had explained it very well. And of course, when you're looking for explanations in strength of materials, you go back to the basics, back to the real source, Timoshenko. So I found this in an old Timoshenko book in which he explained it, and the book was old enough that he wasn't working with bolts, he was working with nails and 2x4s. But nevertheless, the principle was the same, because when you have two pieces that you want to fasten together so that they act as a beam, you have to have enough fasteners to carry the horizontal shear stress for that to happen. So this is a method of calculating it. And this is the VQ over IB shear stress. And so I set up a little problem and worked through it here, and these are the dimensions, which I think most of them are given on the with the figure, I believe. Yeah. Now, this is the type of beam, and I just came up with a kind of an artificial type thing to illustrate the point. You have a 400 pounds per inch loading, and it's 50 inches long, and it's made up of two 1-inch plates, and you're wanting to hold them together with bolts, and you're going to have two at each spot. So you want to know how far apart your rows of bolts need to be. How far can you go and still hold the thing together? So that's this E is the spacing here, because you see what you actually get when you apply the moment. Then you have the horizontal shear surface here, which in this case is the neutral axis of the beam, and you need to calculate that stress and determine the bolts. All right, you get the reactions to the beam, and then you get the moment. It's a uniformly loaded beam, so it's WL squared over 8. And then you determine a value here, because you also have to check bending stress to make sure that your bending stress is all right. Even if you do carry the shear, it still has to hold it in bending. So I just took a guess at the diameter bolt and said, well, I'll use a 1/2-inch bolt in this and see how it works out, and then I'll calculate it. So if you go into this, the VQ over IB, remember the V is the vertical shear at the point. Q is what's called the statical moment, which is the area above which you're wanting to check the stress, above that shear plane, times the distance to its centroid. That's a statical moment. Then, so the Q here was I calculated was 3 inches cubed, because it is a area times the distance, so which makes it cubed. Then you go in and calculate the moment of inertia. In this case, I left out the diameter of the holes on this because I was just doing it rough. And of course, one of the things that you should do in the final calculations, you actually deduct for the diameter of the holes in order to get the proper moment of inertia. Then I went in and said, for no bolt hole reduction, I'll have this stress. Now that'll be across that shaded area back in the figure there, which was 6 wide, so it was 6E. So I solved for the number of pounds that I would have that I'd have to react at that point. All right, if I take 2 1/2-inch diameter grade 5 bolts, good for about 10,500 pounds apiece, and I divide this total load into that and solve for E, I get 2.8 inches maximum spacing between row of bolts. So then I went back and said, okay, I'll use 9/16 bolts and with a clearance hole, and now I'll deduct for the holes that I'm taking out and calculate a new I, and then go in and calculate the shearing stress, take that to get me a value involving E, and then solve for E using the higher allowables for the 9/16 bolts, and I get 2.94 inches for row spacing. Now, you could optimize on that and do all sorts of things, but what I was interested in here was just showing how you would do it, because none of the books that I had, actually, strength material books, showed that the way it was supposed to be. I didn't think so. Now, you still have to go in and check for beam bending and bearing stress calculations. And notice also that thin structures would have to be checked for inner rivet buckling, because if you have thin sheet and your fasteners are spaced too far apart, the sheet can buckle in between fasteners under compressive load. And you've heard that statement about a little knowledge is a dangerous thing. I was telling a guy that this could happen one time at Martin, and he was taking strength of materials, so he said, nah, that can't happen. So I went to see one of the old timers to find out how to get out of it. And he said, well, just go up and tear a page out of his notebook. That'll prove the point, because you see, if you take a page and you pull it this way, the sheet will buckle between holes before it tears up. So I did that, never had any more trouble with the guy. He went back to his strength materials book. So that's how to carry the horizontal shear loads. Now we go into bolted flanges with O-rings. Now granted, that is a science within itself, but we'll cover it here just to let you know that you have to do this with bolted joints. O-ring compression in a flange is usually just a small portion of the total bolt load. And of course, the O-ring groove is sized to give a specific range of compression on it when you go metal to metal on the flanges. Now, for most O-rings, this compression value is like a minimum of 10 to a maximum of about 30% of the unloaded cross-section diameter. And of course, the flange surfaces have to be smooth to assure sealing without tearing up the O-ring. And the fastener spacing must be close enough to keep the flanges from separating. That's one of the things you have to watch about. Now, granted, in most cases, it's not a problem. And of course, this has just a general design practice. You machine the O-ring groove in the cheaper of the two mating flanges, because if the machinist cuts the groove too deep, the part's scrapped. So you want to make sure that it's in the cheaper of the two flanges, and so you can throw it away if you need to. And if you need a dovetail groove to hold the O-ring in place during assembly, disassembly, that also can be machined in. Now here is a generic O-ring joint, and there's the O-ring. Normally the only thing you got to worry about is having a smooth enough finish on this mating surface in that area that it doesn't chew up the O-ring, and have enough fasteners to keep the flanges metal to metal. Now if you go to bolted flanges with flat gaskets, then you got another problem. You need to squeeze the gasket to seal it, but on the other hand, you don't want to squeeze it so much that you yield it in compression and ruin it. So now you have to look harder at the amount of load that you're putting in with your bolts. Now, a lot of gasket manufacturers will give you a pounds per linear inch or something for a flat gasket, so that you know then by your bolt spacing how much you need to put in to get the thing to seal. At least that gives you a minimum load that you have to have. And then of course, you have to look at the compressive yield of the gasket to see whether you're putting too much load in or not. So usually the best thing to do on that is get the information from the manufacturers, because they know their product well enough to give you the proper values that you can use. And of course, we'll have some things in subsequent sections on what to do where you have gaps on flanges. Now here's a regular flat gasket joint, and one of the things you normally do with gaskets too, if you're in the automotive world, you use some sort of a gasket cement sealer or something of that nature on them to stick them in place while you're putting the joint together. And we have loading curves for the flat gaskets in the appendix, which you'll get one of these days here in the near future. And the flat gasket joint design, Bickford has quite a bit more coverage on it. And so between that and the manufacturers, chances are you can come up with enough information for that. Now, gasket loads in flange joints. Leaks usually start at the point of maximum flange bending, which is midway between adjacent bolts, where the gasket's not compressed enough to seal. A lot of you have run into that in the past with valve covers on cars. they don't have enough fasteners in them, and you have cork gaskets, so you tighten them down and the thing will bow and leak in the middle, and so you have you put cardboard under your car. And so to increase the load at the midway point, you can look at 3 different ways of doing it. One is to increase the number of bolts, increase the flange thickness, and increase the initial bolt torque. So those are 3 things that you can look at, all of which have their advantages and disadvantages. The increased number of bolts, since deflection is proportional to the cube of the span between bolt centers, that cuts way down on the deflection of the flange. And so, so adding a bolt at mid-span gives you a cut of 8 on the deflection and increases the gasket load. The only thing is you increase the cost because you've now added another bolt hole. Increasing the flange thickness. Now, since flange deflection is inversely proportional to the cube of the flange thickness, you double the thickness, it decreases the flange deflection by a factor of 8. So that is a good thing, except that you increase the weight and the cost of material. So that's another thing that you have to weigh. Now, increasing the bolt torque is the cheapest way of doing it, but if you increase it to a certain point, the flange can bend in the middle because you're compressing it down under the bolt and it'll allow it to bow up in the middle where it'll leak worse. So particularly if you have a soft gasket, like the cork gaskets, you get leakage. So, and if the bolt is near the yield point, a further increase in torque can't be made unless you use bolts with a higher strength. So one of the El Cheapo ways that you can do on this is put extra diameter type washers under the bolts to spread the load out just a little bit. Sometimes that'll stop them from leaking, but that's not something you'd want to put in an original design. Now getting into bolted flanges for glass windows. The reason I put this in is this is a special one, and we've used it around here on designing of windows for pressure vessels, because normally you don't think of a window as needing much in the way of gaskets, and they more or less just slap them in and they're done with it. They're in cameras and things of this nature. But where you need to use sight gauges, or in our case, actually in CM1, use cameras through glass, now you wind up with an optical quality window that costs several $1,000s that you need to make sure that nothing happens to it. So the way to make sure nothing happens to it is that you kind of pad it all the way around with rubber to keep it from touching the metal. And then, of course, one of the things about it, in ours in particular, was that the fastener design becomes a balancing act to seal it without overloading it, because you don't want to overload it. And the other thing, too, is glass is so brittle, the thing that causes it to fail, of course, is surface imperfections, and you can't afford to scratch it with anything. So it has a coefficient of thermal expansion about 1/6 that of metal. So if you put it in and you have a temperature change, now you have to put enough padding around it of some sort to allow it to be compressed by the material around it, or expanded and so on, without leaking. So that's a balancing act. So you sandwich it in flat rubber gaskets with a bumper strip around the outside of the window to keep it from direct contact with the metal. And then the balancing act is to seal it so that it won't leak, but yet not compress it too much. So we have a typical design shown in figure 35, which you can go and put up there. And now, This is a model of what we actually used in CM1, except that the one thing that I didn't show, just for clarity, was the O-ring that we had there. But you see, here, I'll use this one, it's a little clearer. Here is the window. You have a bumper strip around the outside. Now this is something that's not a sealer, it's just to keep it, when you drop it in the socket that it's in, or the well there, to keep from touching it. You have rubber gaskets on the bottom, you have a round gasket there, and then you have one on top. Now what you're doing here, you're going metal to metal with this top flange. Now you have to use the tolerances of both on machining of this and machining of this surface in order to make sure that you can put that window in there, size your gaskets properly, and in some cases you have to grind them to get them to the right diameter, or I mean right thickness, because the rubber is not close enough tolerance. Put it in there, bolt it all down, and seal it without hurting anything. So that is a special design within itself, and of course with your bolts you have to make sure that they're strong enough to go metal to metal and load the thing up without overstressing the bolts. Now the effect of friction in a clamp joint. In most cases, friction forces between clamp surfaces are not included in the shear calculations. The reason being that it's too hard to determine what they are. Because if you've got oil or grease on the surfaces, your friction coefficient could be real low. If you've got striations of some kind on it, it could get real high, but you really don't know what it is. So for that reason, you normally don't include the axial force of the bolt times the coefficient of friction as a shear capability that you have. Now, there are a few cases, and the next page will show there the actual friction forces that you can get. You see you have a bolt preload of P, and so you take that times the coefficient of friction on this surface and this surface, and you got two forces here. That two of these N forces, and the N is the friction load, which is the normal load times the coefficient of friction by definition. So in some cases in the construction world, they actually use this friction load when they are doing the joint calculations, because they count on it, but it's not something that you would normally count on because it's too unpredictable. Now the compression cone of a bolted joint. We covered this earlier there in the stiffness section, but in the appendices we do give more stuff on it, and here's something that I alluded to earlier, the bolt joint relative stiffness calculations. And most of the ordinary designs are not a big requirement. It's just that where you have, say, small areas that you would want to, like for instance, if you had some, now if, one of the things that would be a real problem, if you have a bushing type thing around the bolt or a spacer or something like that, then you better go in and check that one real fast, because you could get into trouble. But if you have, say, steel, and you're using steel bolts, chances are the joint is going to be stiff enough that you don't have a problem with it. You can look at it and take the method of least work on it, calculate a circular model for the stiffness. If that is satisfactory, then go no further. Now, if you were bolting, say, through soft aluminum, copper, something like that, then you would probably want to do some joint stiffness calculations to make sure that you're not in trouble. But in most cases, you can get by with a minimal amount of joint stiffness calculations. Now, bolting of dissimilar materials. As I mentioned earlier, in the Centaur case where you went from room temperature to minus 300 or something like that, with dissimilar materials, there you got a real problem because of the differential thermal expansion and contraction of the materials. Because aluminum is, let's see, something like 3 times, I believe, isn't it, the on thermal? Something like 3 times as high a coefficient as steel is.
I thought it was around twice.
And copper is way up there, so if you're bolting up a copper joint and you have a temperature change, you got to be real careful on it. But then the other thing that you needed to watch for is the galvanic corrosion, because unless the mating surfaces are insulated from each other, and that was one of the reasons why the magnesium has kind of gone out of vogue, because how do you insulate it satisfactorily that over a period of 20 years, if it's using an airplane component, that it's going to stay insulated? Because a lot of these organic type things that they use for insulation, the sealers that they put around rivets, bolts, and stuff like that on airplanes, over a period of years can deteriorate and moisture. And the other problem with the fasteners on an airplane is that most of them, you're looking at heads sticking out. So if you have a crack that is starting at the edge of the hole, it has to come out quite a ways before you can see it. So that has caused a lot of problems there. The other thing that you need to look at is the yielding of softer materials, because if you are, say, using a high-strength bolt in aluminum and you crank that up too much, you can actually yield the aluminum in compression under the head without doing anything to the bolt. So, and then, of course, you got to check the strength at the temperature extremes, because, like for instance, aluminum falls off drastically at only 250 degrees, whereas steel, most steels will go up to 700 and up before they start falling off in strength. So if you were tightening up an aluminum joint and you ran it up to, say, 250, 300 degrees, you could get yielding real easy under the heads of the bolts. Now, maximizing the effective length of fasteners. Of course, when we discussed the stiffness ratios, the effective length of the fastener was mentioned. And this is important on the differential expansion contraction. So it may be necessary to add a spring or a Belleville washer under a bolt head to increase its effective length enough to satisfy the design so that it won't loosen up. And the deflection, of course, is the PL over E, so you increase L, you're doing all right on it. In fact, on the exhaust system on some of the Ford trucks, they actually have a big spring on the bolt that holds the flange to the catalytic converter. It's put on there, I think, to take the temperature differential that you get between the materials, because you can go from room temperature up to about 1,300 degrees or something like that on them. Okay, we'll take a break here for now and come back up with the match drilling of fastener holes, which is an important one.